In this video, we are going to be performing Casagrande's log of time curve fitting method as well as Taylor's square root of time curve fitting method examples. So on my website, I'm going to go to the CE 445 resources and I'm going to go ahead and download the curve fitting example raw data. And so this is just an Excel sheet we're going to open up. Okay, so it's still working on opening. This is something else. Here we go. There we go. Okay. So it's taking this a while to open, isn't it? All right. So here's our data. It doesn't seem like too much. Notice that we've got a time column in minutes and we have a vertical dial reading column in inches. We're also given an initial height of the specimen, and then the final height of the specimen is the specimen's final height at the end of this load increment. So the first thing I'm going to do is I'm going to go ahead and calculate an average height of the specimen throughout the duration of this testing. So we can say equals average, and then we'll just take an average of these two numbers. Okay, and so we see that the average height throughout the duration of this test is 0.96 inches. So I'm going to go ahead and do some formatting along the way. There we go. And because it's a consolidation test, it's a pretty safe assumption to note that this is a doubly drained test. So we're going to say HDR is the average height divided by 2, since it's a double drain test, and the longest drainage path is going to be half of the average height. Okay, so let's go ahead and get started, and we'll start with Casagrande's method first. Okay, Casagrande's method. All right, and remember, Casagrande's method is log of time. Okay, so what I'm going to do here is I'm going to go ahead. This is the raw data. I'm going to go ahead and select my data. And I'm going to insert a scatter plot, and I'm going to generally, when you have data and you're wanting to connect the data markers with some kind of curve, I connect them with straight line segments. And the reason why is that the curve segments could give you some artificial curvature. Remember, Excel is it's basically connecting the dots as best as it can. And if you're not careful, Excel could, accidentally put some extra curvature or humps in the data that's not really there, but it looks like it could be there to Excel. So to avoid that, it's usually better to connect the dots with straight line segments. Okay, so we have this, and we can give it a chart title if you want. We just call it Casagrande's method. Oh, I have trouble spelling. All right, and we'll go ahead and add axis titles. Okay, again, I'm trying to format this as I go along. And remember, this horizontal axis is going to be time in minutes on a log scale. Okay, so we'll change that to a log scale in just a second. And then the vertical axis is the dial reading R in inches. Okay, so let's go ahead and make this a little bigger so we can see it better. All right, so what I also like to do is I like to format this a little bit better. So there's a lot of dead space on this graph, so I'm going to right click on the vertical axis, and I'm going to set the minimum to 0.08. That way that'll spread the data out a little bit better and it looks a little nicer. It's already looking better. And we want to get the time axis on a log scale. Okay, so I'm going to right click on the horizontal axis and change this to a logarithmic scale. You may get a little warning there, and that looks a little bit more correct, like it should. And again, you want to format this a little bit better, so we can, let's see, we can right click on the horizontal axis, format axis, and we can say vertical axis crosses at an axis value of 0.1. And so that'll just move that vertical axis over to the left a little bit. And I guess we can add some minor grid lines, just so we can maybe read some things better. So where are our minor grid lines? Missed it. There they are, right there. Add minor grid lines. Okay. And so, you know, they're kind of a gray color here, but they're there. All right. And this is our plot for now. Okay. So, what is Casagrande's method say? Well, the first thing it says is establish two tangent lines, one from the primary consolidation curve stem and the other from the secondary consolidation points, okay? So the primary consolidation curve stem is right around here, okay? So to establish some tangent lines, what I'm going to do is I'm going to go insert, and Excel is great for this. You can hit insert, and you can insert lines in here. Let's see where this version of Excel looks a little different to me. It's not that, not that. You would think I would be familiar with this because this is my computer, but as you can see, I clearly don't use Excel on this computer as much as I probably should. Where are my lines? That's not it. There we go. Okay. Right under illustrations. I think on other versions of Excel, that's somewhere over here, and it's not called illustrations. Anyway, when I went to illustrations, shapes. Either way, you're looking for a line shape, and we have the line here. Okay, so I can put this line through here, and the great thing about this is it's a shape, so you can kind of you know, adjust this as needed. Okay, you can move it around, and I'm going to change it to a red line just so we can, you know, see it a little bit more clearly. Okay, and so that's going to be through the primary consolidation data, and then we're going to add another tangent line through the secondary consolidation data, which is right around here. Okay, I'll make that maybe red as well. Okay, and so remember, secondary consolidation is occurring right here in this neighborhood. It's where the data changes curvature and it becomes more curvy. And then our procedure says where these two lines intersect is assumed to be where we have 100% primary consolidation. And so this point is called R100 and the time is T sub P. So I'm going to grab maybe an arrow here under my shapes, and I'm going to go to where they intersect. Now, if you want to, you know, keep this arrow moving like vertically, like I'm showing here, hold the shift button. If you're not holding the shift button, this thing could be at any angle. Hold the shift button and drag your arrow down, and then you can land it right there. And we see that, you know, TP is probably about 11 minutes. It's just past the 10-minute mark. Okay, so maybe down here I'm going to say T sub P in minutes is equal to 11. All right, and we'll do some formatting here later. Okay, and again, that's 100% primary consolidation, and the reading at this point is R100. So you know, you can go back and insert another line, and you know, hold shift and drag that to the left, and we can add some minor grid lines here as well so we can hopefully see things better. Okay, and what is what is the 100 reading? Well, I would say 0.09, 0.092, 468, 0.098 inches. Okay, 0.098 inches. Okay, so that's R100. Next, we want to determine the dial reading at 0% consolidation, which is going to be R naught. Okay, the first part of the consolidation curve is assumed to be parabolic. Okay, so what we need to do is we need to arbitrarily choose times T1 and T2 that have a 4-to-1 ratio. All right, so here's what I'm going to do. Since I have, this point right here already, that's going to be time 0.1. Okay, time 0.1. Log scales can't plot the 0 point. That's why that's not showing up here. So I'm going to arbitrarily start with this point right here. I'm going to say, let's call T1 0.1. Okay, minutes. So I'm going to say, call T1 in minutes 0.1. And then we're going to choose, let's go ahead and do some formatting while we're at it. And I'm going to go ahead and choose that. So then T2 is going to be equal to 4 times T1. Okay, and so that's a pretty easy pick right there. Okay, and then you want to mark off those dial readings as R1 and R2. So if you come up here, T1 was already given to us, right? That's 0.1, and then R, what's the R reading there? It's probably 0.14246, 0.147. Yeah, look at that. There it is, 0.147. Okay. So we'll say R1 in inches is 0.147. Okay. And we'll do some formatting as we go along. Obviously, on a homework assignment, you want to format this very professional looking. And then R2 is going to be the reading corresponding with this time 2 of 0.4 seconds. So where's 0.4? Well, you've got 0.1, 0.2, 0.3, 0.4. Remember, you're on a log scale. So, if you want to help yourself identify things a little bit better, 0.4, 0.2, 0.3, 0.4 is about right here. I'm just going to drop a little circle there just to help me identify that. And then we can, we can move this on up right here. Okay, maybe give it a different color. Okay, and so what is R2 going to be? It's going to be 0.14 inches. Okay, so 0.14. Now, Casagrande said do this a couple of times. Okay, do this a few times so that you can get some better data. Okay, better end result. All right, and so we can go ahead and calculate. We can calculate an R naught value from this iteration. Notice I'm doing some drag and drop here so I can keep my formatting of my subscripts. So R naught will be equal to R1 minus R2 minus R1 minus R1. Okay, and so that's our R naught value. I'll go ahead and give a little highlight there. Now, again, Casagrande said do this a few times. So let's do it just one more time. Okay. So how about this time we pick? So let's see, iterate once more, and I'm going to say let's choose T1 to be 0.4 this time. Okay. How about we do that? How about we choose T1 to be 0.4? And so T2 is going to be equal to this 0.4 times 4, okay? So we get 1.6. And so coming up here, we can go insert, and again, we're just doing this again. So where's 1.6? Well, 1.6 should be about probably right here. It's hard to see, right? Remember, this is on a log scale, so you got to be careful, all right? This is 1, this is the number 2. This minor grid line is 2, so 1.6 will be right around here, all right? And then we're going to insert maybe another arrow. We're going to come on up right here, and then maybe just make that green. And then we're going to move over to the left, and what do we get here? About point, let's see, move to the left, 1, 2, 2, 4, 6, 0.126 roughly. Okay, 126. Sorry, let's go ahead and just copy paste this. Copy paste is your friend, remember that. So R1 now is 0.14, and then R2 is 0.126. There we go. And again, I made my life easier by copying and pasting. Now check that out. The R naughts came out to be calculated the same. And again, you know, Casagrande says recommend do this a couple of times so you get consistent R naught values. Okay. Now we need to compute R50. All right. So I'm going to go ahead and do some formatting here. Make my cells look nice and professional with subscripts. There we go. Here we go. Okay. Now we need R50. Okay. So how do we calculate R50? Well, we're just going to calculate the average between R naught and R100. So we're going to say equals, and we'll say, you know, R100 plus R naught divided by 2, and there's our R50, okay? And from here, we know from a handout what the time factor, capital T50, is. If you know from your time factor handout table, that's 0.197. Oh, my Excel jumps around sometimes. 0.197. Okay. And then from here we can calculate the coefficient of consolidation C sub V, and we can calculate this in terms of inches per minute as we say it's capital T50 multiplied by HDR squared. We already have the drainage height right here, squared, and then we can divide all of this by little t50. We haven't obtained that yet, I guess. So let's go ahead and get that here, little t50 in minutes. So how do we do that? Well, we go to R50, which is 0.126. All right, it's the average. Yeah, 0.126. Say insert. We'll insert a shape 0.1246 here, and then we'll insert another shape. This just so happens to land right back on a point we're familiar with. So it seems like T50 is about 1.6 minutes. 1.6 minutes. 0.6, there we go. Stretch that out a little bit. And then we take this CV formula, I had started typing it, divide by T50, and here is our C sub V factor, and of course we can format this accordingly, and this is the answer we were looking for, is how do we determine C sub V, and here you go. So it's kind of a coincidence that this R50 happened, it just so happened to correspond with this particular R2 value. Notice that both of these are 0.126. That's not always going to happen. That's just a coincidence that happened based on the current numbers we have for this data. Normally it won't happen that way. So that concludes Casagrande's method. So I'm going to go ahead and save this video, and we'll create a second video for Taylor square root of time method.